Welcome to Thursday Night Physics. Tonight we're going to be looking at GCSE electricity. So we're going to split this into several sections. Firstly, we're going to look at what electricity is, then take a deeper dive into the ideas of current, voltage and potential difference, and resistance. Once we've got our heads around those particular concepts, we're going to think about how they behave in series and parallel circuits, and after we've done that, go through a series of exam questions, particularly looking at anything to do with calculations. So, to begin with, what is electricity and what's sort of the purpose of it? So, particles have charges, okay, so they can be positive or negative, and electricity is just the flow of these charges. So if there are electrical charges flowing, travelling from one place to another, then that is electricity. You may have come across the electrical pathway during the topic of energy, and this is the idea that we can transfer energy from one store to another through electrical pathways. So through the movement of electrical charges, energy can be transferred from one store to another. The classic example of this is that you can have a battery which contains chemicals, so a chemical store of energy. This then causes charges to flow. They then transfer their energy to components, and then it is transferred to a different energy store. This flow of charges is sort of more precisely called the current. So the electrical current, very much like a water current, is just the flow of something. So we could say that current is the rate of flow of charge. Now, these charges could be positive or they could be negative. At GCSE, pretty much every single question is going to be about the flow of negative charge, which is electrons. So if we put together a very simple circuit, okay, so here we have our simple circuit. We have negative and positive. Then we're actually going to be thinking about which direction this current would be going. Now, conventional current, well, this is the flow of positive charge. But electron flow, the flow of the negative charges, is going to be the opposite of this. So conventional current actually goes from positive to negative. So this is talking about the flow of positive charges. So current, conventional current, goes from positive to negative, even though it is electrons that are flowing, which are negatively charged, going from negative through to positive. Now, why do these charges flow? Well, they flow because of the voltage or the potential difference. These two things do mean something slightly different, but at GCSE they are basically interchangeable. Now, the voltage is the energy being provided to these charges. This is their electric potential energy. So if we think about electrons are all going to try and repel each other because they have the same charge. So if they're built up over here, they're going to have more electric potential energy, so they're being provided with this energy, which is then going to push them around the rest of the circuit. So the voltage or potential difference is the energy per charge. So if you are providing more energy to the charges, that means they have a higher voltage. Okay. The final of our big three that we need to think about is resistance. Now, resistance is just anything that is opposing or trying to slow down the flow of charge. So it is anything that tries to slow down the flow of charge. So when we're talking about these three quantities, we've got our current, which by the way has the symbol of I and the unit of amps. We've got our voltage, or potential difference, with the symbol V, with the unit of volts. And we have our resistance. This one has the Greek letter omega for its units and the symbol of R. And this is measured in ohms. Okay. So these are the three main quantities that we have to think about when we're talking about electrical circuits. We can think about electricity in the form of several different models, which I might talk about later. But really, you can just think, if you understand how these three things work together, then you can understand electrical circuits. So you've got current, that is the rate of flow of charge, which usually is electrons, which are negatively charged. We have voltage, which is the energy that is being provided to each charge, and the energy that's going to be transferred from one store to another via the electrical pathway. Then we have resistance. This is what the energy is going to be transferred to, and is anything that is going to slow down the current, anything that's going to resist that flow of charge. Okay. Now, these three units, these three concepts, they are all bound up in the idea of electric circuits. So an electrical circuit is going to have, at its bare minimum, it's going to have some kind of energy source, a power supply, and it's going to have some other kind of circuit, and they can either be in two forms, a series circuit or a parallel circuit. Now, if we look at this circuit, okay, we're using circuit symbols here, so we've got a cell and we have two resistors. You can tell that a circuit is a series circuit if you can take your pen and trace around all the different components without leaving the page or going back over yourself. So if there is one continuous loop, then it must be a series circuit. Everything comes one after the other, they're all connected up together, and we can trace around without having to leave the page. Now, parallel circuits, or if something is in parallel, they look a little bit different. So now I'm going to connect my two resistors up in parallel with each other. So you know something is in parallel if you have to leave the page to be able to trace over everything without going back over it. Okay? We cannot do this in one consistent loop. So this is our parallel circuit. Again, we've got our power supply and we have two components, these being resistors. By the way, if anyone has any questions at any point, please do pop them in the chat and I'll do my best to answer them. So we've looked at series circuits and parallel circuits. We now need to have a think about how our three different concepts, our three different quantities, act within these circuits. Because this can be one of the main ways that you're tested on it, one of the big things that you have to try and understand. Right. So if we look now at a battery, a battery of cells, and we say that we're going to have a power supply, we're going to have an input voltage of 6 volts. We're then going to have two resistors, one there and one there, We don't know what the resistance of these resistors is currently. I'm going to put an ammeter in there and an ammeter in there. So, ammeters are components that measure current. They have to be placed in series with components to be able to measure the current through them. We're also going to put in 2 voltmeters. These measure the voltage or the potential difference across a component, and these have to be placed in parallel to the component or components you're measuring the voltage across. So we've got our 6 volt supply. So this is our total voltage. So I'm going to call that V total is equal to 6 volts. Okay. So the first thing we're going to think about is the current. So we can measure our current with ammeters, and ammeters tell us what the current is going to be at that location. In a series circuit, the current is going to be the same everywhere. The current in a series circuit is the same everywhere. So if we call that A1 and that A2, we know that we can say that A1 is going to be equal to A2. Now, why is that? Why is the current going to be the same everywhere? Well, if you think about it a bit like water, if we have a pipe and water is entering that pipe, it can't leave the pipe any quicker than it goes in, because where would that extra water come from? So here we have our series circuit. We have one consistent pipe. The current is flowing through. You can't get extra current from somewhere. So it has to be the same everywhere. But what about when we initially switch this circuit on? Say if we had a switch there, well, surely when I immediately switched on, we've got the electrons flowing, so it's going to be faster in one place than the other. No. This is a misunderstanding of the idea that the electrons are stored within the battery. That is not the case. Electrons are in every part of that circuit already. There are electrons in the wire, there are electrons in the resistors, there are electrons in the ammeters. All that flipping that switch does is it provides a push to those electrons, so it provides them with energy that then gets the electrons to travel through the circuit. So that way, the current has to be the same at all places. It's all being provided the same push. Electrons can't suddenly enter the system, so the current has to remain the same. So we can say that if we connected any ammeters in this circuit, it would be consistent. Okay, what about the voltage? The voltage, again, that is the energy per charge. Now, when an electron is pushed around, all its energy, all the energy it's being given, is going to be transferred to the components in the circuit. So if our supply, our total input voltage is 6 volts, then if we think about this as V1 and that as V2, we can say that the V total is going to be equal to V1 plus V2. And if we had any more components in here, then that would just be shared between all of them, because the energy is being shared between each component. One model for electricity is the rope model. The idea that if you had some rope, that would be like your circuit, and if you passed it through your hands, you're providing some resistance to that rope moving. Now, if you grasped onto that rope, you would be providing friction to it. So when that rope moved, energy would be transferred from the rope, or the person pulling and pushing the rope, to the hand. Now, that energy is going to be shared between all the hands that are holding onto that rope, onto that circuit. So the energy is shared between all the components in the circuit. Now, which of them is going to get a larger share of the energy? Well, is it going to be the one that's holding on lightly or the one that's holding on hard? Well, hopefully from your own experience, you know that if you hold on to it hard, you'll be provided with more of that energy. There'll be more friction, so more energy transferred. So the higher the resistance, the bigger the share that component will get. So if we say that this one has more resistance. Let's say that this one is a 20 ohm resistor, so ohm being the units for resistance, and this is a 10 ohm resistor. Which one is going to have the greatest energy transferred to it, the greatest voltage drop? Well, it's going to be V2, this component, because it has a greater share of the resistance, so a greater share of the energy is going to go to it. Okay, now, but how can we work out how much energy is going to be transferred to it? Well, if there is 6 volts in total, and the total resistance is 30, well, we can work out what the different proportions are going to be. But we'll get to that in a moment. What is the total resistance of this circuit going to be? Well, if we think about this from the perspective of an electron, which components is it going to be resisted by on its journey? Well, it's going to be resisted by both. For it to get around the circuit, say it starts here and it needs to get all the way around, it's going to go through both the 10 ohm resistor and the 20 ohm resistor. So for a series circuit, the total resistance, or R total, is equal to the sum, or the adding up, of all the resistors in that circuit. So R total is going to be equal to 10 ohms plus 20 ohms. So in this circuit, R total is going to be equal to 30 ohms. Okay. Now, we've got the total resistance, we've got the total voltage. Now we're going to think about the total current. To find the total current, we need to use an equation. And we're going to use the equation of Ohm's law, which is that V is equal to I times R. Or V total can be equal to the current times by R total. Let's look at it. We've got V total, 6 volts. We've got R total, 30 ohms. We've got 2 of the 3 pieces of information, so we can work out the third. So V total is 6 volts is equal to the current times by 30 ohms. We need to rearrange this equation to find the current. So we want to get I on its own. So we divide both sides by 30 ohms. So 6 divided by 30 is going to be equal to 6 divided by 30 is equal to 0.2. Then the units for current, amps. So we know that the current is equal to 0.2 amps. So now we can do a mathematical test to check whether more is going to go to the 20 ohm resistor than the 10 ohm resistor. We can use this equation again, Ohm's law, to check it because we've now got this. So if we want to know the potential difference, the voltage through that component, we can say, let's go to a different page. We can say that V is equal to I times R. So V is equal to 0.2. Let's look at resistor 1 times 10. So the voltage across resistor 1, so V1, is equal to 2 volts. V equals IR again, so V2 is equal to 0.2 times 20. So V2 is equal to 4 volts. Now we can check, do these still remain true? V total, 6 volts, is equal to V1, 2 volts, plus V2, 4 volts. 6 equals 2 plus 4. Looks right to me. So this is how you do this for a series circuit, because bear in mind, we can do this in one loop. The ammeters are in series, the voltmeters are in parallel. Now, let's have a look at a parallel circuit. So for this one, we're again going to have our battery with a supply voltage of 6 volts. We're then going to have two separate branches. On one of them, we will have two resistors, and in the other, we'll have one resistor. We'll say that this one is 10 ohms, this one is 20 ohms, and this one we'll leave as an unknown resistance. Right, what are the circuit rules for these? What are the circuit rules in a parallel circuit? Well, to begin with, we're just going to ignore this section. We're just going to think about what would happen if we were going back to a series circuit. If we put an ammeter there and an ammeter over here, what do we know? Well, this is a series circuit, so we know that that one is going to have the same current as over there. We know that this is going to get a larger share of the voltage than this one. Right, let's reinstate this loop. We said before that the current in a series circuit has to be the same everywhere because you can't get extra current from somewhere. The same logic applies when you think about branches. Let's say the current is going positive to negative, so it's flowing down here and then it's splitting at this junction. So at this junction, we can see the before and after. So we've got one set going in, two sets coming out. So if we said that the current was 1 amp, we could say, so if there is 1 amp of current going through this way, we know, would an ammeter on the bottom part of the circuit read the... No, that's what we're looking at the moment. Okay? We could say that if there is 1 amp going into the junction, well, there must be 1 amp going out of the junction. So if we think about this in context of water for a second, if we had a water pipe here, okay, which was then flowing into two separate water pipes, water going in has to equal water going out because there's no extra water there. So let's say that 0.6 amps flows down this direction. How much would flow down there? Well, we know that the current in equals current out. So we could say 1 amp is going in. We know 0.6 is going this direction. So 1 minus 0.6 is going to be 0.4 amps. Does that work? 0.6 plus 0.4 equals 1. Brilliant, we've got it. Okay? So we can work out what the current through this is going to be. So if we did put an ammeter down there and an ammeter in here, we would know that 1 amp is coming in. We know that at this junction it's splitting. 0.6 amps is going that way, and 0.6 amps 0.4 amps is going down there. Okay, so that is how current will work in a parallel circuit. Let's have a think about the voltage. How is the energy shared between this? So to do this, I'm going to sort of scale up the wires to make them a bit chunkier so that we can see into them. This is, of course, just a representation, a model of what's going on. It's not actually the full idea. So, I'm going to say we're just going to look at a couple of charges. We're not going to look at all of them. We're just going to track the progress of those charges. So these triangles, they are representing components, and this arrow is representing the power supply, so where the charges are getting their energy. And we're going to think about just two charges. We'll have a blue charge and we'll have a green charge. And we're going to track their progress. So at this point, they are provided their energy by the power supply. Or rather, the power supply is pushing them with giving them a certain amount of energy. So they start off 6 volts and 6 volts. So that's the amount of energy per charge. That's what they've been given. They've got to drop off all their energy before they make it back. So, green charge. Well, the green one doesn't go down this. The current is splitting. It goes down here, drops off at 6 volts. It is now at an energy level of 0 volts. It's got no more energy. It goes back and then is provided with more energy. This is a model. This isn't what actually happens, but it's an idea to help you think about it. The blue one, well, it's given 6 volts. It travels down here. It splits, travels here, provides 6 volts to this component, carries on, and returns. So what I'm trying to say is that because it is different charges going down each branch is provided with the total energy. So the voltage across each branch in a parallel circuit is equal to the supply voltage. Now, you don't have to actually calculate how resistance works in a parallel circuit. The only thing you need to know is that the resistance is going to decrease if you add in a branch. So, let's go to a new sheet. If we had a circuit like this, okay, let's call that 10 ohms. The resistance, the total resistance, will decrease no matter how large a resistor you put in parallel. So even if we put 1 mega ohm resistor in here, so really high resistance, the total resistance will still decrease. Now, the way you could think about this is with a traffic model. So say there was a road, and it's quite a busy road, lots of traffic goes down it. Even if you add a little lane that's now going to the same place, the traffic overall is going to flow better. Because even one car that doesn't go down this traffic, this road, and goes down the other one, is going to free up the system. This is why adding in parallel branches is going to increase the current and decrease the overall resistance. Right. That is plenty of theory. Let's have a look at this in practice. Let's go through some exam questions. So these are for AQA GCSE. Let's have a look at them. So, an electrical circuit is shown in the figure below. We've got a battery, we have a 20 ohm resistor, a 10 ohm resistor, and 0.4 amps of current going through it. The current in the circuit is direct current. What is meant by direct current? So this isn't something I've covered, but direct current is all about the direction of flow. You have direct current and you have alternating current. So what is meant by direct current? Direct current is current that always travels in the same direction. Alternating current, as the name suggests, is something that goes back and forth in its direction. A battery provides a constant direct current or a DC power supply. The equation which links current, potential difference and resistance is potential difference equals current times resistance. Calculate the potential difference across the battery in the circuit in the figure above. 3 marks. Right, let's have a think about what we've got. So Have a quick look at this. I'm going to be going across to there. I'm just going to quickly draw it, and then we'll have a look at it. So we need to find the total supply voltage. We need to find what V total is. So to do this, we need to use our circuit rules. So we've been told the equation V is equal to I times R. We're looking for V total, which is going to be equal to the current, which is the same everywhere in a series circuit, multiplied by R total. So the first thing we do is think, is this a series or a parallel circuit? Well, I can trace all the way around, so it's a series circuit. So V total is equal to I times the current times R total. R total for a series circuit is the sum of the resistors in that circuit. So 20 plus 10, 30 ohms. Okay, so we've got our total resistance. So V total is equal to 0.4 times by 30 ohms. 0.4 times 30. V is equal to 12 volts. So in setting that out, I wrote out the equation. I wrote out the equation to find R total for a series circuit. I then substituted those values into the equation and got my answer, and remembered to write my units. So there's your 3 marks for that question. Right. The equation which links current, potential difference and power is equal to current times potential difference. Calculate the power output of the battery in the figure above. Give your answer to one significant figure. So, power is the rate of energy transfer. The rate of energy transfer. So because of that, we can think about what we need to use. So if the voltage is the energy per charge, and the current is the rate of flow of charge, the rate of flow of energy is going to be the voltage multiplied by the current. So to find this, we're going to use the equation. P is equal to I times V. So I'm going to substitute, I'm going to write out the values I know. So I is equal to 0.4 amps and V is equal to 12 volts. Now that I've written those out, I'm going to substitute them into the equation. P is equal to 0.4 multiplied by 12, which is equal to 0.4 times 12, 4.8. And the unit for power is watts. Is this the end of the question? No, because it said give your answer to one significant figure. Currently, we have 2 significant figures. So a significant figure is any non-leading non-zero number. So we'd need to round this, so we had one significant figure. So it is 5 watts to one significant figure. Right, we've come to the end of the plan section. So if anyone has any questions, now would be a great time to ask them. If you're watching this later, feel free to add your question in the comments and I'll see if I can either give you a link to a video, or if it's an easy one, I'll try and reply to your comment to help. I'll be running Thursday Night Physics every Thursday, as the name might suggest, at 7 o'clock, and I'll be alternating between GCSE and A-level content. If you have found this helpful, please consider liking the video because it, makes me feel happy. And if you would like to watch more and be reminded about them, then please do subscribe to the channel and click the notifications, the bell icon, so that you're notified when they go live. I'll just wait for a minute or so to see if anyone does have any questions, but then I'll be finishing there. So I hope you found this helpful, and I will finish shortly. If you have any requests for topics that you would like covered on one of these Thursday night physics sections, then please do also leave that as a comment. Right, I think we'll end there. Have a very good Thursday evening, and I will hopefully see you next week.